I start?
Yeah, please go ahead.
Okay, so let us continue this discussion. I'll skip over this slide. It is not uh, highly motivated given the constraint of the time that we have. We'll now generalize this BPSK modulation, which is a one-dimensional modulation because uh, the two possible transmitted symbols are located on this one line, to a 2D modulation. Basically, if you recall, we had used this generic symbol SI plus JSQ, J times SQ. BPSK just uses SI. SQ is always 0. So the next modulation called QPSK modulation actually uses both SI and SQ. So for BPSK, we had two symbols at +1 and -1, let us say, if A is equal to 1. For QPSK, similarly, there is +J and -J, assuming again that A is equal to 1. This is known as quadrature phase shift gain. The x-axis is same as BPSK, but now there is another BPSK on the y-axis. And they together make SI plus JSQ. The radius of the circle again is same as square root of the energy per symbol. This is just one possible arrangement. There are other arrangements possible where you can have QPSK transmission. The main idea is that there should be 4 different symbols, and these 4 symbols should be separated by 90 degrees on a unit circle, meaning that all these 4 symbols should be at the same distance of A, or square root of ES from the origin, and you go from one symbol to the next along this circle by adding 90 degrees. That is why it's called phase shift gain. You are shifting the phase. Okay. So BPSK transmitter can send only one bit at a time, whereas QPSK now you can do 2 bits at a time. So if 2 bits are 1, 1, then you say that SI and SQ is plus A divided by square root of 2 plus A divided by square root. 1, 0 is given by the second line of SI and SQ. 0, 1, third line, and 0, 0, the last line. Basically, SI and SQ are the Cartesian coordinates of the symbol points. If you recall, that is giving us the quadrature notation of SI and SQ in phase and quadrature. When you actually upconvert this symbols which are at the baseband, the transmitted signal will have this cosine and sine terms. But remember, we said that up conversion and down conversion, we are assuming that they have been cancelled at the front end of the radio. And so we are just dealing with this complex symbol, which is SI plus JSQ. Or we are dealing with the magnitude and the phase representation. But the magnitude A is the same for all 4 symbols of QPSK. It is also the same for 2 symbols of BPSK. So QPSK and BPSK do not make use of the magnitude to transmit information. The way they transmit information is by changing the phase. Why? Because the phase is this tan inverse of SQ divided by SI. It is that phase which changes by 90 degrees whenever we go from one QPSK symbol to its neighbor. That is what this slide says. Okay. Now, at the receiver, again, there will be some noise that will be added now because this is a two-dimensional symbol. The noise also will be two-dimensional, Ni and Nq. So for BPSK, as you could see, the noise was getting added and it was perturbing the transmitted points. For QPSK, this type of perturbation will happen. Is that fine? But actually, there is something wrong with this slide. This chart is incorrect. What is wrong with it? Yeah, it should be a two-dimensional noise. See here, for the 2 points along the x-axis, the y component of noise is always 0. Similarly, for the 2 points along the quadrature axis, the x component is 0. The noise doesn't know that it has to make either x or y 0. It will always be non-zero in both the dimensions. And so the actual diagram looks like this. Instead of lines around the points, now it will be cloud around the points. So you might ask, okay, fine, we accept this, but then why did you not draw for BPSK? You might ask, yeah, why did I not draw cloud around these 2 points? Okay, so that is something that you need to think about and give an answer later on. It's not something that I'm asking you to do right now. Okay, so this is how the QPSK, yeah, correct, Matthew, that is correct. Because there is no SQ component, although in reality there will be a cloud, we throw away the quadrature component of the noise entirely because it does not affect the BPSK or the on-off keying symbols. For QPSK, we cannot do that. Depending on which constellation points we transmit, there will always be some cloud around it. And again, we apply the maximum likelihood scheme, which is same as minimum Euclidean distance. Suppose we receive in the two-dimensional plane, we receive a received signal at the point where my cursor is. I will again make bigger. So if my received signal is here, then I'll calculate all these 4 vectors, E1, E2, E3, E4 in the manner shown. And then I'll say that this is the most likely symbol to have been transmitted because its distance to the received symbol is the closest. And so once I apply this minimum distance detection scheme, I can draw decision regions similar to how I drew it for BPSK. For BPSK, it was just a point halfway between the 2 transmitted symbols. Here, the decision regions are perpendicular bisectors of the lines connecting 2 consecutive symbols. So this is showing those perpendicular bisectors. It basically divides the plane in phase and quadrature plane into 4 quadrants. And then depending on which quadrant the received signal falls in, you decide the corresponding symbol. This assumes that the 4 symbols are like what it is shown here. The only thing that changes if you suppose transmit QPSK in some other alternative arrangement is that this uh, decision boundaries get rotated in the same manner that you rotated the transmitted symbol. You could transmit symbols like this, which is what I had shown here. For this, the perpendicular bisectors are simply in phase and quadrature axes, and the decision regions are simply the four quadrants. There is another scheme that is called binary frequency shift keying, where bit 0 is transmitted using frequency F1, bit 1 is transmitted using frequency F2, and this F1 and F2 occupy orthogonal dimensions, and therefore the transmitted constellation looks like this. Again, the any preference for two types of constellation? Absolutely no preference. You can have either one as long as remember again, the error probability will depend on the distance between two consecutive points, two consecutive transmitted points. If you take any one of the two constellations, so if I take, let's say, this constellation, I get the second constellation by just applying 45-degree phase shift. So if I apply 45-degree phase shift, obviously I'm not causing the Euclidean distances to either shrink or expand. And therefore, the performance will remain identical. So from performance standpoint, there is no difference. Okay. This is showing the binary frequency shift gain scheme. So you still transmit one of two symbols, not one of four anymore. But those two symbols, unlike BPSK, are transmitted at the 2 points in green circle, which are shown here. Assuming they are equally likely and assuming that the noise is Gaussian noise, then again, the same observation applies. The decision region becomes the perpendicular bisector of the line connecting these 2 points, which is the one shown in red. And anytime you are closer, you are in this region R2, you decide S2 was transmitted, otherwise you decide that S1 is transmitted. The BPSK generalized, the QPSK generalized BPSK, M-array PSK is a generalization of QPSK. So this is showing 8-array PSK. PSK, there is no information being conveyed in terms of amplitude. So it's all about phase shift key. But now we are trying to transmit more bits than just one or two. 8-array PSK transmits 3 bits per symbol. To transmit 3 bits, it needs 8 symbols. And those 8 symbols are located like this along a circle. Again, the squared radius of the circle is the energy of that symbol. And then the mapping is what the designer will set. Maybe one way is that when you get 0, 0, 0, 3 bits are zeros, you transmit this symbol. When you get 0, 0, 1, you transmit this symbol, so on and so forth. How do you transmit, for example, this symbol or that symbol or that symbol? You go back to that magnitude and phase representation. Magnitude remains the same. All you change is the phase of that cosine signal. For this scheme, again, the decision regions will be perpendicular bisectors, and so they'll seem like pizza slices. And so whenever you get received signal which is in this particular thin wedge, you decide that symbol number 2 is transmitted, because all the points within this shaded region are closer to symbol 2 than any other symbol. Further generalization is possible, which will lead us to quadrature amplitude modulation, or in general, amplitude and phase shift gain. Here we are changing both the amplitude as well as phase. Okay. And if it is M-array modulation scheme, basically we take a block of k bits, where k is log base 2 of m, and use it to pick one of those m symbols. So this is the general diagram. Suppose capital M is 64. When M is 64, we will have 64 symbols. Every time we pick one of those 64 symbols to transmit, which means that every time out of all the bits that are coming in, we pick 6 bits. That 6-bit sequence will give us a unique number going from 0 to 63. And so we map that number to one of those 64 symbols. So let's say if M is 4, then we can just do QPSK. This is showing the bit assignment. If 0, 0 is received, then you transmit this symbol, otherwise this, like that. 8 PSK we just looked at. Basically, you take 3 bits at a time and use those 3 bits to pick one of the 8 symbols. 16 are the amplitude phase shift gain. So now we have 16 points as shown here, which means that we will take 4 bits at a time. Those 4 bits will give us one number from 0 to 15. Each of the 16 points are labeled with one of those numbers. This is an alternate way to show the same design, which is called 16-array quadrature amplitude modulation. This is an example of 64-array quadrature amplitude modulation. And it doesn't have to stop at 64. You can go to 128 or 256 or 1024, 512. Okay. So we can do some very simple math and evaluate for 64-array QAM what is the average energy per symbol when the distance between 2 consecutive symbols is 1 unit, as it is shown here in this diagram. So when we do the calculation, we realize that this 64-array QAM has 3 types of symbols. You look at these 4 symbols in the very middle, their energy values are the smallest. This is what I'm calling PS inner. Then there are 10 points. I'll label them 1, 2, 3, 4, 5, 6, 7, 8. No, not 10, sorry, 8. So this 8 points, 2 here, 2 here, 2 here, and 2 here. They also are along another circle, which is at a radius of square root of ES middle. And then the 4 points on the outer have the largest energy, 1, 2, 3, and 4. So when the distance between the two consecutive symbols is 1 unit, then innermost symbols have the energy of 0.5. You can calculate the energy of the middle points. The 8 middle points have energy of 2.5, and the outermost point have the energy of 4.5. Why 4.5? Because the the coordinates are 1.5 away, units away. So 1.5 square is 2.25 times 2 becomes 4.5. And so the average energy per symbol, if you just plug in the math, it turns out to be 2.5 units, which means that in general, the distance between two consecutive points for 60 quam is ES divided by 2.5, square root of that. The reason I'm saying that this is because we can then use this distance expression to evaluate the error probability performance for 16 quam. This I have done in detail in the rest of the slides, but let me not get into that because of the sake of time. I have maybe another half an hour left, so and I want to cover another topic, which is non-coherent modulation. So I will stop my PowerPoint presentation at this point, and I'll go to my next presentation, which is uh, going to summarize this detection method. Okay, so I'll in this set of slides, the new thing that I'll do is provide a quick overview of non-coherent detection method, which is sometimes also known as square law detection method. Okay, I will not spend a lot of time on this first part because this is very similar to what we have already done. And then I'll go to the second part, which is the non-coherent detection. Okay. So this is the general Bayesian rule that we have already talked about. We have talked about the maximum a posteriori rule and maximum likelihood detection. And we have seen that in general, the detection problem in the context of a communication signal can be written using this simple diagram where we, at the receiver, we get a vector R of symbol coordinates. And using that, we have to determine what the transmitted vector S could have been. We have seen that, so we saw this for single dimensional BPSK case, which generalizes to multi-dimensional case that conditional probability of R given a particular transmitted signal in case of Gaussian noise is given by this multi-dimensional Gaussian PDF. This is just a multi-dimensional generalization of the Gaussian PDF, which we have seen earlier for BPSK. And the map rule maximizes the posterior, whereas the maximum likelihood just maximizes these conditional likelihood functions. So if you take the map rule and maximize the posterior, do the logarithm and cancel out the identical terms, the final rule becomes what is shown at the bottom of the slide. Okay. If the priors are equal, meaning all of these P of n values are the same, then the map rule becomes same as ML. And then you can ignore this first term. What remains is just the second term. And that basically becomes the minimum Euclidean distance detection, which is what we have already concluded. But here we are saying that that minimum Euclidean distance detection applies whenever R and S M are belonging to some higher dimensional space. Now, one simplification of this ML is that you don't need to even calculate the distances. You expand this this vector norm formula, and it turns into this. Now again, R hat R is independent of M, small m, so we can ignore that. And so the two terms that remain are Hermitian transpose Sm, Sm Hermitian transpose Sm. So R Hermitian transpose Sm is nothing but the projection of the received vector onto the mth signal vector. And Sm Hermitian transpose Sm is nothing but the energy of that particular symbol. And so we can implement ML by doing basically a projection operation. Now, in addition, if all the symbols we know ahead of time, they have the same energy, then we don't need to even calculate this. We just calculate R Hermitian transpose Sm, which is basically saying that we take the received vector R, project it into all of the M symbol vectors, and then decide on that symbol vector for which this projection is the largest. Okay, so this is yet another way of implementing ML rule. Obviously, when priors are not equal, we have to do this full calculation. Okay, so that is the map and ML rule. This projection operation is sometimes also called match filter receiver. You can implement it using either match filter receiver, or you can actually do the Euclidean distances and minimize it, or you can implement decision regions. There are multiple methods of implementing the ML rule. And then the map rule is you can do it in two stages. You always implement ML because ML is always going to be a part of math. So you implement ML, and then you say that, okay, the transmitted symbols are not equally likely, then I add that additional component which is that log base to a log base E of P of M. The assumption is that in doing all that, we have assumed that the carrier frequency Fc is known very well. Even the timing is known very well. And other aspects such as phase and the coefficient of the channel due to multipath fading, etc., are all totally and completely known at the receiver. In the actual design, the knowledge of these signal parameters is not trivial. And so today, when the engineers world over design the next iteration of the communication systems, they already know all of this maximum likelihood and maximum a posterior technique. Their focus is now on how to do the carrier frequency estimation very well, how to mitigate Doppler, how to mitigate imprecise local oscillator effect, how to design in presence of phase uncertainty, etc., timing uncertainty. So there is a lot of elaborate design that happens to compensate for all of these parameters which are actually variable. Now, there is another approach which says that let's not do any of that. Okay, it's a very simple approach which says that I'm not going to worry about specifically in this particular example, I am not going to worry about removing the phase offsets that the channel might introduce. In that case, how can I do demodulation? Okay, so consider this particular representation of the receipt signal, A of n, exponent of j theta n, exponent of j phi n, plus U of n. A of n is the amplitude modulation for the nth symbol. Theta n is the phase of the nth symbol. So if it is, let's say QPSK, A of n is going to be the same, but theta will change every time in multiples of 90 degrees. Phi of n is the uncertain phase introduced by the channel, communication channel, which we will say, I don't want to deal with. And then U of n is the noise. This approach of non-coherent demodulation says that assuming that the channel phase phi of n does not vary from one symbol to the next, and then in addition, let us assume that this A of n is a constant as it is for QPSK or 8PSK, etc. Then I can write S of n in this manner. Dependency of phi over n went away because I'm just assuming that for two consecutive symbols, phi is constant. A of n, I got rid of it, replace it by square root of ES because that also doesn't change with symbol index n. The clever idea that we are going to discuss now is, what if we at the receiver do S of n times S conjugate of n minus 1? This is called differential detection. Okay. Why? Because let us evaluate S of n times S conjugate of n minus 1. Remember, S of n, we wrote it like this on the previous slide. So S of n times S conjugate of n minus 1. First term will be ES e to the power j theta n minus theta n minus 1. This phi part got cancelled out because of the complex conjugation. The second two terms are both square root of ES times some complex phasor times U of n. This term gets multiplied with U conjugate of n, U of n gets multiplied with this term. And then the last term is Un times U conjugate of n minus 1. So basically, this Q of n will have these four components. What we are going to do is we are going to ignore this fourth term. Why? Because individually this U of n itself, because it is noise, it's going to be hopefully not too strong. Let's say its strength is 1% of the symbol strength. Then when you do Un, U conjugate n minus 1, that term will have a will have a strength of 0.001%. Basically, its strength further diminishes. So we can almost always safely ignore that. So then what remains is just the three terms of this Q of n expression. Now, for simplicity, we will divide both the right-hand side and the left-hand side by square root of ES. And so finally, we get the expression that is shown in the middle of the slide here. Okay, for this one, I don't think I can make my cursor to be bigger. Anyways, now what happened because of this scheme? Let us see first of all what happened in terms of noise. Previously, I had only one noise component. Now I got two noise components, Wn plus W conjugate n minus 1. And these two are, roughly speaking, independent and identically distributed random variables. When you add them, basically the power of the noise increases by a factor of 2, or the standard deviation goes up by square root of 2. So instead of calling them as summation of two IID noise components, I will call it as some noise component which has been scaled in the standard deviation by square root of 2. I will further normalize, and then this theta n minus 1 I'll call delta theta n. And so that final answer that I'm getting is that the received signal after I do this operation Sn times S conjugate of n minus 1, I can write it as, I can write it in this manner. Square root of Es divided by 2 e to the power j delta theta n plus V of n. Compare it with this one. What is the difference? First difference is that the square root of Es becomes square root of Es divided by 2, meaning that the variance of Un didn't change. Basically, my SNR dropped by a factor of 2. Why? Because I'm getting affected by two noise terms now, which are adding. So obviously my SNR goes down by a factor of 2, which is captured by this square root of Es becoming square root of Es divided by 2. But more, so that is the penalty I pay, but on the other hand, the advantage that I get is that this phi term went away. I don't have to be bothered about knowing the phase of the channel. Here there is no phi term. And so that is the advantage of this, what is known as non-coherent modulation. It removes the distortion due to the channel, assuming that that distortion remains constant across two consecutive symbols. And to get benefited, I will transmit information in this delta theta n term, not in the absolute theta n. So the bits incoming to the modulator don't determine the value of the actual modulated phase, but they determine the value of the phase with which the signal changes, going from the one symbol to the next. So if incoming bit is 0, then you set the phase of the next symbol same as the, okay, so this is, okay, this is for the coherent case. Whenever incoming bit is 0, you set theta n equal to 0, otherwise you set theta n equal to pi. Transmit +1, here you transmit -1. This is the standard BPSK. Non-coherent BPSK or differential BPSK, you start with any phase of the transmitted signal. Actual value doesn't matter. If the incoming bit is 0, then you continue to transmit at the same phase. If incoming bit is 1, then you shift the phase by 180 degrees. Okay, so this is showing the performance of the scheme. The blue is the coherent BPSK. Its performance is going to be always better than this differential or non-coherent BPSK, which is given in the yellow curve. Differential BPSK typically suffers from roughly about 3 dB of performance penalty. Sometimes it is slightly less, especially at higher SNR. Now, this non-coherent approach, which does not require to be concerned with estimating the channel phases, it is not proprietary only of BPSK. You can apply it to QPSK, you can apply it to 8-array PSK, so on and so forth. Basically, the idea is that you take incoming bits and use it to determine whether to change the phase of the next symbol compared to the current symbol. You don't use the 2 bits to determine the phase of the absolute phase of the current symbol. That is the coherent scheme. Non-coherent schemes always determine the delta changes that are introduced. Okay, I will take maybe 10 more minutes and introduce one more technique called differential frequency shift keying. Okay, so in binary frequency shift keying, suppose there are random phase that we don't want to estimate and remove. You remember binary FSK that I had shown, I think, in the previous hour? There are 2 frequencies, F1 and F2, and corresponding to whether you want to send bit 0 or bit 1. And coherent binary FSK, its demodulation happens exactly using the minimum distance detection rule. But when additionally there are some phase variations that we do not want to estimate and get rid of, then we have to worry about a signal model which is shown here. If you expand this out, then you see that there are actually 4 terms, cosine and sine. So we need 4 different functions: cosine of f1, cosine of f2, sine of f1, and sine of f2. And S1 of t can be written using cosine of f1, sine of f1 in this manner. These are showing the multipliers of f1, f2, f3, f4. For S1, f3 and f4 are absent. What are the multipliers of f1 and f2? They are given by square root of EB cosine of phi1 is this term. Square root of EB sine of phi1, which is this term. The minus sign is already part of f2. Similarly, for S2, f1 and f2 are not present, and it's only f3 and f4. Square root of EB cosine of phi2, square root of EB sine of phi2. So now our signal has to be sent through a match filter with all of these 4 functions. Which functions? f1, f2, f3, f4. Basically cosine and sine of f1 and f2. So we will assume equiprobable symbols and maximum likelihood scheme, and we'll see what happens. So probability of received vector given S1 and phi1 is going to be a Gaussian PDF given whose expression is given like this. R is now going to be 4-dimensional vector. Why 4-dimensional? Because we are taking the received vector and evaluating its correlation with cosine of 2 pi f1, sine of 2 pi f1, cosine of 2 pi f2, sine of 2 pi f2. When S1 is transmitted, correlation of S1 with cosine of F2 and sine of F2 is 0. Basically, the mean terms goes away. Mean of the received signal corresponding to R3 and R4 becomes 0. And therefore, the conditional PDF is given like this. When S2 is transmitted, the conditional PDF now has P2 terms of cosine, sine, and cosine of Phi2 that determine the mean corresponding to R3 and R4. And the mean corresponding to R1 and R2 is 0 because we are transmitting S2, not S1. Right? So you will see the difference. This is the conditional PDF for S1. This is the conditional PDF of S2. Now, this is, we can still not work with it because of this phasor terms, phi1 and phi2. And so we have to marginalize it. This is a more detailed math that we have to do to evaluate the marginalized PDF of R given S1, R given S2. They require this integrals. Here the common term capital K is given by this expression, R1 squared, R2 squared, R3 squared, R. Where is it coming from? R1 square, R2 square, R3 square, R4 square. And EB, where is the term EB coming from? Well, when you expand out this expressions, EB cos square phi2, EB sin square phi2. They add up, it just becomes EB. Same way here as well. So that is where this other term EB is coming from. Now, it seems like this is a little complicated, but there is a function called modified Bessel function of zeroth order, which actually exactly represents this integral that we are trying to evaluate. And so these complicated looking expressions become simply this, where I0 is the modified Bessel function of the zeroth order. Now, remember that in maximum likelihood, if conditional PDF of R given S1 is greater than R given S2, then we choose symbol 1 over symbol 2. Which means that if this term is greater than this term, then we choose symbol 1. Now, to determine which of the two terms is bigger as a function of R1, R2, R3, R4, first of all, K is common for both the sets, so it cancels out. So all of that complication that we had here doesn't matter. Secondly, even I0 function, that modified Bessel function of zeroth order, that also goes away because it is a monotonic function, meaning that if R1 plus R2 square is bigger than R3 plus R4 square, then only this I0 function will become greater. It will never be that R1 plus R2 square is smaller than R3 plus R4 square. But once you plug them in I0, suddenly the output becomes stronger. That doesn't happen with this modified Bessel function zeroth order. That is this monotonicity property. So mathematically, I am completely justified in ignoring even this I0 function. And I just look at it, the argument of that function. Once I look at the argument, I say that, okay, n naught term is constant, it goes away. I don't care about square root because square root is also a monotonic function. And I can square both the sides. 2 scalar 2 is also constant, cancels out. EB is a constant, cancels out. And so finally, boils down to deciding whether R1 plus R2 square is bigger than R3 plus R4 square. This is called square law detector. All we are doing is we are measuring the energy at the output of the filters that are tuned to F1, and that is this R1 plus R2 square, versus the filter that is tuned to F2, which is giving us R3 plus R4 square. So non-coherent reception of frequency shift keying symbol binaries FSK has a nice interpretation. It's coming from this elaborate math that we did, but the final answer is very easy to understand. That you pass the receive signal through filters centered at F1 and F2. What are those filters? Filters centered at F1 are this cosine and sine filters. They give us R1 and R2. Filters centered at F2 are these two filters. They give us R3 and R4. You pass the received signal through those filters, then calculate the energy at the output of each filter. What is the energy at filters centered at F1? R1 plus R1 squared plus R2 squared. Then filters are centered at frequency F2. The total energy produced by them is given by R3 squared plus R4 squared. And then we select that symbol for which the corresponding filter exhibits bigger energy. And the nice thing is that this derivation that we did for binary FSK also extends to M-ary FSK, meaning that if you have M different frequencies that we are transmitting from, then we will have M different filters, calculate the energy, and pick the one which has the highest energy. And we can do some error evaluation analysis, and it turns out that this non-coherent reception approximately degrades by about 3 dB from coherent BFSK reception. Okay, so with that, I conclude my topic on non-coherent detection, and I am just on time. It's about 4 p.m. So thank you.
Yeah, so thank you, Professor Yashwasada, and I hope the audience have enjoyed these series on fundamentals of communication system theory, and possibly the participants who already have a background in communication system theory, maybe these series would have act like a refresher course. And for those who are seeing this for the first time, probably you are now motivated to learn more about the same concepts being applied in quantum communication, which will be starting in the next week. So a big thanks to Professor Yashwasada for accepting as the speaker to deliver his expertise on this particular topic. Thank you.
Okay, thank you.
So we'll end this session and we'll meet again on Monday, same time at 2 p.m. Thank you all.
Okay, bye.
Bye.